So today webinar is one of our series of webinars at Ozen Engineering. The title of our webinar today is Do Not Remesh, Morphing Shape Optimization in ANSYS Mechanical. The presentation will be presented by Professor Marco Biancolini. He's from Italy. We will be presented at the end of this introduction as in cooperation with Ozen Engineering. Let me give you a quick introduction about Ozen, what we do at Ozen Engineering. We basically use this physics-based simulation to solve multidisciplinary engineering problems using industry-leading CAE technologies. We use all finite elements package using ANSYS for multi-physics, finite element analysis, as well as computational fluid dynamics. Ozen Engineering is a channel partner of ANSYS in North California, and we this year we became the partner of the year for the second time in the last 5 years, and we also have been taken as a lead channel partner and distributor in California. What we do at Ozen is we basically provide software sales, training, technical support, and we also provide consulting services in all the physics of engineering. We provide all these services for fluids, for structures, electronics, multiphysics. We also have the VR services. We combine it with finite element analysis, as well as a cloud computation using Ozen Cloud or ANSYS Cloud. We also recently provide services for optics, which is one of the recent software added to ANSYS package. We have webinars scheduled. This one is the last one in this series. You can see here all the previous presentations or previous webinars we provided in different topics, in electronics, in fluids, in mechanical, topology optimization, heat transfer, and other topics. All these topics, if you are interested in any of these, you can find it on this link here on ozeninc.com webinar library. You'll find the recording of all of this. There will be new webinars will be posted very soon on our website for some coming presentations and webinars. Now there is a trial, a free trial version of ANSYS Cloud that we encourage our users to use. It's basically ANSYS provide a free service of ANSYS Cloud recently just to experiment the HPC usage using the cloud in case your machine or computer does not have the specifications or doesn't have the hardwares, and you need to run some big some big models. You can run it on ANSYS Cloud. It's very easy. You can contact us and let you know how to use that if you're one of ANSYS customers. ANSYS simulation software is very easy to help you to design your products, ensure that you can deliver the product that work as advertised for every product, every order, and every customer. So if you are using any tools, we can help you with that. If you have any question in consulting services or selling the software or buying the software, you can contact us on info@ozeninc.com or visit our website ozeninc.com. By the way, right now we're hiring. We're looking to hire mechanical and electrical engineer. So if any of you or somebody you know is interested, please let them send our resumes to us on info@ozeninc. The presenter today is Professor Marco Biancolini. He's an associate professor of machine design at the University of Rome, Tor Vergata. Professor Marco started his research career in 1998. He has a long industrial experience in mechanical engineering, and for today, he's the author and the owner of the RBF Morph software technology, which is recently became partner of ANSYS since 2009. So you're going to have the presentation by the main source and the main person who invented this technology. So I think it's time to pass the presentation to him. If you have any other question, please contact us at info@ozenengineering or support@ozenengineering. All right, so to not waste more time, Professor Marco, I'll make you presenter right now. So please share your screen and unmute yourself.
Perfect. Can you hear me?
Yes, I can hear you, and I see the screen as well.
Perfect. So first of all, many thanks for your introduction, and let me start my presentation here. There we go. So as you can see from this very first animation, mesh morphing means that we can change, adapt shapes, and we can do that keeping the same mesh. This is the outline of the presentation of today. I will give you first a short introduction to RBF Morph, and I will tell you what are the ANSYS products that we support. A very short introduction about the math that is under the hood of RBF Morph software, so radial basis functions. Then I will provide an overview of our mechanical module and of a collection of industrial applications. Then we will go a little bit more in detail on a couple of applications. So it will be the optimization of a turbine blade and the use of BGM, that is an automatic self-sculpting tool. And then we will conclude the webinar of today with an hands-on showing in detail how it works and how to set up a practical application using RBF Morph technology. So first of all, our origin, it was 2007 that the change of rule in Formula One was planned. So changing totally the shape of the car. So the need of restarting from scratch and the need of CA tools to explore many different shape variation was really compelling. And so our first morphing technology that the inception was then with name of RBF Morph was the answer, and it was a first driven project. And after this first adoption, we put the product on the market, and very soon after the presentation, we has been awarded by Most Innovative Approach using simulation methods at the ANSYS conference in 2009. We are good at make parametric CAE models. So what is important is that with our technology, we do not only mesh morphing, but we make parametric, the CAE model, ready to run. So the traditional workflow in which you update the geometry, you do a new mesh, and then you solve is replaced when you use RBF Morph. You need just a baseline model ready to go. Then you put morphing parameter, and then you can automate the process. Like in this example, in which the aerodynamics of this motorbike driver is inspected. You have here 45 different variations, changing the height, the angle, and the deflector angle of this case. So let me explain with a very, very simple example. This is a glider. This glider got a problem at the junction between the fuselage and the wing. And so using RBF Morph, this is a 30-second video, you can work with the baseline CAD. You have the baseline CFD model, and then with the UE of RBF Morph, this is the FLUENT version, you can introduce shape parameters, in this case 2 shape parameters, and then you can steer the optimization so that you go for the optimal solution. You can reconstruct the optimal CAD geometry and exit then the workflow. This is what we used to do with our mesh morphing technology, and in this case of the glider, you can see the effect. This problem of separation was almost totally removed, getting an increase of efficiency of the wing of 35%. Well, I has been already introduced, but let me tell you a little bit more about us. My name is Marco Evangelos Biancolini, and we offer indeed a synergy between the academia and the CAE professional world. As an academic, I am an associate professor of machine design at the University of Rome, and I have a team of students, and I work with students across Italy and Europe, and I am coordinator of different research projects, including research projects funded by the European Community. On the CAE business, I am an expert of advanced CAE workflow, especially on vertical automation for shape optimization. I'm the author and the owner of RBF Morph software, and I am an honorary member of TechNet Alliance since 2013, and I cooperate with many ANSYS channel partners worldwide. In the middle, you can see the cover of the book I have recently authored with Springer, that is about the math of my technology. This allows us to offer better solution because we are an ISV, but we have also a very deep understanding and knowledge on the problem. This is an example of a demonstrator on HPC funded by Fortissimo project from the European Community. And here you can see for this Lamborghini car how the airbox of the 12-cylinder engine can be optimized using RBF Morph, then 3D printed, and then getting 5% more horsepower on the car. This is what we can typically do. So let's speak a little bit more about our partnership with ANSYS. We are an ANSYS preferred solution partner, and we are partnering indeed since 2009. So we offer two integrated solutions. That is one, the FLUENT done, the one of the video previously shown. That was our first product released in 2009 that is fully integrated within FLUENT, interact with Workbench with the adjoint solver, and allow to handle also multiphysics. Then we have the software that I'm going to explain more in detail today. That is our ACT extension that has been released in 2015 on demand. First adapter was Chemkin, an Italian company, is fully embedded in ANSYS Mechanical, allowed to have a parametric mesh morphing, and it benefits, as I will show you, of the underlying geometry or on auxiliary geometry. It is also working with workbench meshing. It means not only mechanical. Here there is a very short video of a case that I will show you in detail today. This is 30 seconds. We have a turbine blade. We have a baseline stress analysis. We want to reduce the stress at the spot. Here you can see the accelerated setup of RBF Morph. I will show you this slowly at the end of this webinar into the hands-on. And in this case, we get the stress reduction acting on two shape parameters. We use the X in this case, and at the end we have a new cat representation. So a little bit more details about our ACT extension. As you understand from the video, it's integrated in the tree of mechanical. So you have the same look and feel of mechanical and the same interaction logic. Is technically speaking written in Python and XML as all the ACT, but it interacts with an advanced RBF library that is very powerful and accelerated for shared memory parallelism and also for GPU. And we have a hierarchical logic, And such hierarchical logic allow to work with basic shape modification or to create new complex shape modifications if you want. So here we have a list of the main features of our software. We can use linear and cubic RBF spline to have direct control, acting directly on the FEA mesh nodes. It works for all solutions. Whatever can go with mechanical can be managed by RBF Morph. So even a very complex workflow, linear, nonlinear, static, dynamic, whatever. It works for 2D and 3D. And for whatever boundary condition, contacts, and so on. You can define geometrical targets, so you can connect curve to curve, surface to the surface, and you can have basic shape modifiers. You can move, rotate, you can offset on the normal direction of the surface, you can scale parts, and so on. And whatever is in the tree can become a workbench parameter that can be then used to steer shape optimization. We have a fast RBF mesh morphing parallel solver that allows to work with very large model. Recently, we introduced new features. We have improved surface projection that now comes with an advanced direction control. So you can go on the target normal, on the source normal, or you can see the normal direction. You can apply manufacturing constraints. I will show you this later. You can do automatic shape sculpting driven by BGM, biological growth method, and this is something I will show you in detail later on. And you can also apply sequential morphing. It means that instead of having the shape variation from the baseline, you can have that the shape variation are subsequent, and this is very interesting if you have evolving shapes. We have some upcoming features. We are introducing a slide-on surface shape modifier. I will have a GIF to show you. You can sculpt surface importing the adjoint sensitivities that comes for topological optimizer of ANSYS. So we have the ability to use our mesh morphing technology with custom map of displacement on surfaces, and the one coming from topological very powerful. You can use mesh morphing for fracture mechanics as well. So for crack shape of evolution, in which you create the morphing according to what are the solution results, and also automatic update in workbench meshing. Here you have an example of FSI in which you have the mesh of the fluid, the mesh of the wool, and at the same time you have the morphing that is changing the fluid mesh, the structural mesh, and everything is in the sync here. So just a few words about our RBF research part. Fast radial basis function for engineering application is the title of the book, and the technology is something that is continuously evolving and growing since 2007. A radial basis function is more or less an interpolated. So you have simply a sum of weighted radial interaction, an optional poly correction, and can be used to interpolate a scalar function defined in a multi-dimensional space. In this very simple example, you can see how the RBF points can be used to control an height. So you have points on this square that are 0, and you have +1 and -1 on these 2 points. And using the RBF interpolation, you can see how you can have the desired value at the controlling points and the gentle and smooth interpolation otherwhere. So when we use a radial basis function for mesh morphing, we apply fields of RBF, and such field allow to change the shape of a surface or to change the volume mesh that is inside. It's important to say that RBF are recognized to be one of the best mathematical tools available nowadays for mesh morphing. What is difficult is to have fast radial basis function, but we have a very effective and powerful implementation to do that. So what we can do with this technology, let's review a little bit what is possible to get the flavor. Here, some application in the top. This is a way to add a fillet on a mesh using mesh morphing, here with target geometry. And this is an animation showing the ability to slide on surface. We are moving this color, and you can see that even if we have here a tapered shape, the mesh can stay onto the surfaces, so you have this sliding. So is like having a way to update the mesh. It's like a powerful meshing helper tool. We can project onto surface even of complex shape, and this is really important because we can use this to adapt on a manufactured part. We have now a project running on the cloudy factory, that is another European project in which we are using our technology. This is a study we did together with Ozen in the past, and it's about VGA solder joint, and you can see how the ball round shape becomes something similar to a conical one, and allow to get a 22% stress reduction using mesh morphing. Another example here on the automotive field, this is a wheel rim, and we want to reduce the weight while keeping the same safety level. And this is under a very complex workflow. Many different assessments are done on this, and you can get 8% less weight keeping the same safety. This is an example in which we use the technology, as already introduced, for fracture mechanics, and you can simulate crack growth, but you can also use this tool to update crack. You could have, for instance, a very simple shape at the beginning that could be elliptical, and then you can have a complex shape that is coming from experiments, and you can adapt and morph onto a target shape. This is an example in which we can use morphing and with parameters that are not on the RBF morph side, but are on the CAD side. In this case is with the sign modeler, and it's a parametric clue. We have curves that are parametric in the sign modeler that are used as a stencil to create the clue, and this workflow is automated by updating the design parameter that are in the sign modeler, and the FEA mesh that is always the same is updated accordingly. This is full automatic. This is another automotive example that is a connecting rod. This is a titanium-made connecting rod, and these lightning holes are optimized using mesh morphing, using 4 shape parameters, and we get 7% mass reduction. Another interesting automotive application by the University of Catania. This is a race engine of Fiat Abarth, and you have the original shape of the crankshaft, and you want to optimize the hotspot stress that is at this fillet. Using mesh morphing and using 2 shape parameters, you can get 40% stress reduction. This is another example of a SACMI company. This is a complex assembly, and the whole complex assembly is in this case controlled by this very simple surface. So the surface parameters are defined in this case in the Sino modeler and are used to attract the whole complex geometry that becomes parametric but controlled with high precision using mechanical. This is another example from Sakmai company. This is a ductile iron castings. In this case, you have shape parameters that are controlling both the simulation of the process, it has been done by Magma software, and both the structural optimization that is done using ANSYS Mechanical, and the local properties coming from the simulation of the casting result are used to optimize the stress at the hotspot. So after this review of different applications, let me go a little bit more in detail into this turbine blade that has been done together with RINA company, that is an engineering company in Europe, and it's about the stress reduction at the root of a blade, so the optimization of this fillet. So let's describe a little bit this problem. The study is focused on this fillet, this one, and it comes with simplified boundary conditions. So we have pressure prescribed on the pressure side and the suction side, and we have this fixed support here on the up side. The mesh has been refined at the leading edge, at the trailing edge, and at the fillet, and we get a baseline stress solution. And we are concerned about the maximum principal stress because it's the main driving force if we have a crack originated here at the root hotspot. So to tackle this problem, let's go to the basic design criteria that we use for a notch. So for a rectangular bearing bending, we could use handbook data like this one, and we can compute the KT, that is the stress amplification factor at the notch. We know if we use the flow line concept, we know that if we consider this abrupt change and the smooth one, we know that the stress flow line can be gently bent here, and so are less crowded. And the lower are crowded the flow stress flow line, the lower will be the stress amplification. So the problem is that we want to do this not for a flat bar, but for this complex shape. So if we consider a cut here, and we see this from a side, we see something that is very similar to this one, because we have an abrupt change of cross section, and here we have at the minimum section, we have the hot spot. So we want to reshape this fillet, and we need to control this. And to do that, what we are willing to do is that we want to move the beginning and the start of the fillet. So moving this in this direction and moving this in this direction. It's not that easy, but if we go from the basic to the advanced design approach from a notch, let's first of all consider 3D shape that are easier to be managed. For instance, in this bracket, we have a fillet here, and the fillet is straight. In this connector, we have a fillet here, and the fillet is a circle. In RBF Morph, we have a tool to do morphing and to have constraint to keep this axis symmetric to preserve this. So we have a manufacturing constraint. So this can be used, for instance, to optimize this one. At the end of the optimization, you get a shape like this. This is this example. Or for this case, you can change keeping this axis symmetric. This is in bending. At the end, you will have this kind of result. In both cases, you reduce about 20–25% the stress. So if we want to apply the same concept to the root, we need to preserve the complex fillet shape. So we want to have this as a loop. In this example, we achieve this by controlling the curves at the beginning and at the end point. So for the up edge, we move up along the R4, and for the bottom edge, we move along this surface. We have option to have offset from a curve going on to a surface. That is exactly what we want to do this. These allow to accommodate the fillet, and so we control the surface of the fillet, and then we propagate this modification, as I will show you in detail into the hands-on, onto the volume mesh. We add for these two parameters, that is move this edge, so of a certain quantity, and move this loop of another quantity, that is the parameter of the optimization. We put the parameter, and we have, this is a table of the parameters, so we have many different design points. And if we go automatic for this optimization, we have a kind of parabolic shape for the peak stress, and we can look for the optimum, so the point with the minimum stress. You can see here for the explored point how the stress is changing according to the input that we have here. This is the results. Using two parameters, we get more than 20% stress reduction. So we go from something close to 200 to something close to 150. And you can also see how the hotspot is better distributed on the geometry. So we have here a smoother transition. And the CAD model, this is the baseline one, can receive the same morphing action that we have on the mesh, and so we can have the new CAD model that is representing the new shape that is optimal. So let's go now to the second advanced application that I want to share with you today. This is about the BGM sculpting approach. BGM stays for biological grow method. And let's see this method in action with a simple video. So we have a bar with a circular hole that is under traction, and we simply automate the process. So we apply this BGM action on the wall of the circular hole, and what it's happening is that the shape, I will show you a little bit better. You can see that cycle by cycle of this optimization, we start with a round shape. The round shape is changed because of the morphing action, and automatically evolves onto a square rounded shape. We start from 130 megapascal, and we end with 80 megapascal, so with strong stress reduction thanks to the new shape that has been automatically achieved. So let me describe a little bit more in detail such biological grow method. It has been introduced by Mattek in 1990, and you can see at that time it was 2D, it was not a good morphing. You can see the shape here, but the idea is that if we have a structure that is loaded, and the surface can decide to go outward or inward, in the case of the trees trunk, you can only go outward. So it happens that bones and trees and generally speaking biological structure that are stressed usually grow and add materials automatically in the area that are most stressed. This is the reaction of the alive structure to react to the applied stress. So the more is stressed, the more will react, and then the more we will grow. So this is the study by Matek. This is an actual shape, and you can see the cross section, and also from the cross section you can see the history of growth, and the same effect has been here reproduced using FEA, in this case adapting some way the mesh, and you get something very similar. So with our RBF we have this BGM mode, and we can drive the mesh morphing from two phases, and we can drive this according to the stress level. Not only the stress, we can also decide to use other function, as for instance the intensity of a plastic strain, but we generate and we add material according to what we have onto the surface. So the idea of Matek is that the growth volume is proportional to some reference threshold stress and to the actual one. So you will have a positive growth if you are behind such threshold, and you will have a negative growth if you are lower than this. This concept has been refined by Waldman, proposing a multipix approach. One of the challenge of all those meetings is that you need a very good technology to update the structural mesh, because it's a challenge that can be really and easily tackled using advanced RBF mesh morphing. We have, as I have already explained in the features, we have an offset operator. The offset operator allows to move along the normal direction of a surface. So you can, for instance, you can change the radius of this hole simply with an offset. So you can add material, so reduce the radius. You can remove material, so increasing the radius. And this is something that works even if you have a very complex shape. In our software, we have this BGM mode. In the BGM mode, it's in the surface offset operator, and in the surface offset operator, instead of the fixed value, we put here driven value. And in this case, we are using von Mises stress. We decide what is the threshold value, and we decide what is the amount of offset. The amount of offset will be the maximum. It will be normalized during a growing step. This is the maximum extent of growing that I will have on a single loop. So such BGM mode has to be used in a sequential morphing, and for each shape we create a design point. Some very simple example. Let's start with a cantilever beam. We know from basic materials the principles that a cantilever beam to be uniformly stressed should be parabolic. So if we analyze, we see that the loaded edge is not stressed that much, so we can for sure remove material here. And we go with our automatic method to something that is very close to a parabolic shape, and it's very close to an uniform stress condition that is the one we have imposed on the controlled area, that is this yellow one. And here you can see the setup. It's very easy to do, and you can see that this is stress sculpted, and you can see the various frame of the optimization that move to the new shape. In this case, you have 33% mass reduction, keeping the same stress. Here there is another example, trying to use the BGM on the hotspot. In this case, you can have a stress reduction, but you are not preserving the manufacturing constraint anymore. So now it's time, after such an explanation, to go a little bit more into details. We have minutes left to do that, of the case of the turbine blade setup, so that I can show you how it works. This video is also on our YouTube channel. In the one on the YouTube channel, there is also the description. The description here is muted, so I will describe myself. You can see here the mesh, and in the first part of the video, I describe what we want to do, but we have already explained this in the slides, so I will jump a little bit forward to see how RBF Morph is here used. First of all, in this case, I have reopened mechanical, and what is important is that the information that we have is something that is persistent. So when I open mechanical, if I have used RBF Morph, whatever I have done is kept. So I haven't to save nothing. It's something that will be persistent inside mechanical. Here you can notice that if RBF Morph is installed, I can create the RBF Morph object pressing this button. And also you can see that the RBF Morph object is created just after the mesh, and in this case after named selections if they are existing. You can suppress the RBF Morph object like in this example. In this case you will have no morphing, so you will keep the baseline mesh, or you can enable this. When this is enabled, you can have this, you can add into this RBF this is the size of the mesh, it's close to be 500,000 nodes. And you can define, first of all, what is the RBF target. So you can define multiple targets if you want, but the target are the portion of the mesh that we want to move. In this example, we decide to move only a part of the mesh, not the whole one, but the part that is close to the fillet that we want to reshape. To do that, we can use named selection, or we can use direct selection with the mouse. In this case, we also introduce some boundaries to the mesh. So we say that there are fixed area. So we select direct nodes, or in this case on surface nodes, that we want to have a zero movement, so that will be preserved during the morphing action. Then we can control the fillet. We select, in this case, the surfaces of the fillet, and we are nesting. Let's pause this a little bit. As for the fillet, we have a complex modification. We do not add an action directly on the surface, but we nest the tree, and nesting the tree means that the fillet will receive the setup from the children, and the children are the control of this edge that move up and down, and of this down edge that, thanks to a curve offset action, is moved on to the connected surface. So moving this up, moving this upward, allow to get an RBF, a distribution of RBF points that is propagated to the surface, and the surface nodes will move accordingly. Such movement of nodes together with the other nodes will control the movement of the volume mesh. So when I do the morph action, the volume mesh will be controlled by this point, as you can see in the example. So we morph, you see that the mesh is quickly adapted onto the new shape, and you can undo the morph. So you can generate and clear the generated data. In the new version, this is what we have. And so the morphing is automatically triggered if RBF morph is enabled. So you have here, this is the result, because this is the stress distribution that we have with the optimal mesh. It's interesting here to note that even a very small shape variation is indeed responsible of a big effect on the stress. This application, this is an industrial application we did together with RINA, and it's also in the ANSYS blog. So if you browse on the ANSYS blog, you will find all the details of this application. Now, this is in the hands-on a very important moment. You see that instead of using a fixed value, I go back to show you, instead of using a fixed no value of the zeta movement, I have defined zeta as a parameter. I do the same for the other parameter, that is the edge down. I have a fixed parameter, I reset to 0, and then I tell the software that I want this as a parameter, as we used to do with mechanical. I put as a parameter one output as well. In this case, it's maximum principal stress. And now I have parameter. I can explore parameters simply with a table, like in this example. And so automatically I can retrieve the results on all the points that I have. If I say retain data, I can select a point as a current one, and so I can open a points process and I can see what's going on the optimization. Okay, having this is the basic, and this is a simple workbench. And it's worth to say that if I have optimization tool that can interact with workbench, I can steer the parameters. Okay, so in this case we are using the X, that is in particular the response surface optimization tool that we have in the workbench. But here you can use OptiSlang, Mod Frontier, whatever is the optimization tool of choice. So in this example, you can see that we did a DOA exploration of the space to find out the optimum point. And you can see here that the optimum should be this one. And you can see here that we can explore the design space. So you have a surface that is close to be parabolic with the optimum one, and you can do post-processing as usual. The example here is completed, showing the design exploration, and then you can see also, I skip this part, it's a standard once you have shape parameters. And here you can see that we have reconstructed the geometry. In this case, it was in 18, it was with FEA modeler. Now you can do the same action with space claim. And what is important is that you can go out from this process with the desired new CAD. So it's time to move to the conclusions, so that we will have the room also for some question. RBF Morph is an advanced mesh morphing technology that is based on a radial basis functions. You get a shape parametric mesh, but let me say not only a shape parametric mesh, you get a shape parametric CAE model. Our logo, RBF Morph between parentheses, is because at the beginning it was FLUENT, and in FLUENT you have scheme programming in which all commands are by parentheses, and the idea was we need a single line command, RBF Morph shape 1 shape 2, shape 3, and so on, and to get the FLUENT model there. This is exactly what we can do, but for FLUENT and but for ANSYS Mechanical. We can introduce parameters and we can steer parameters using standard optimization tools. We have a very strong integration in ANSYS products. We have an add-on for FLUENT, just shown today with a very quick video. And we have this ACT extension for mechanical. Okay, the original CAD can be updated. The capability that are demonstrated today are, for some example, we have many others. So please have a look to our website, rbfmorph.com. Consider a visit to our YouTube channel and our social channel as well. Many thanks for your attention, and we have some time for questions. Bye.
All right, thank you, Marco. That was very helpful and very useful presentation. And I think you explained a lot of very important features of the RBF Morph. Everybody, please, if you have any question, write it down or unmute yourself and ask your question. For the time being, Marco, I have a quick question. So this ACT extension, is it applicable for 19 version, or is it also applicable for the 2019?
It's currently it works with the current version with the release 1 2019, so okay. 19.3 indeed, and it's very robust. I mean, the same package that we have. It's currently working with 2019 release 1, but the same package works back up to 2.17 version of Workbench. Oh, so it's the same ACT technology. So we have also backward compatibility.
Awesome. Okay, that's good. That's good. Okay. Any question from the attendees? Please write it in the chat area, or just unmute yourself and ask your question. Okay, I don't think we have any further questions, Marco. So thanks so much for this. That was, again, it was very helpful and very educational for us. Thanks for giving us your time and your knowledge. Thank you, everybody, for joining the webinar. I think that will wrap the webinar. Thanks for attending, and thanks again, Marco, for presenting the webinar. I appreciate that.
Okay, it was a pleasure.
Okay, thank you. Thank you, Marco, and thank you, everybody, and have a great rest of the day. All right, bye-bye.